Okay, well, let's start. Today we're going to move on to the topic of imitation learning. We'll do a couple lectures on this topic. And the idea of imitation learning is actually very simple. It's instead of trying to discover everything on your own as a learner, why don't you imitate an expert? So it's kind of an obvious thing to consider. If you try to discover everything on your own, as we've pretty much been assuming so far for the semester, then one of the problems you run into is that if you have sparse rewards, this can take an inordinate amount of time. And furthermore, if the actions that you're doing, for example, involve cross-country driving in the woods, it could be that mistakes that you make along the way could be fatal. So it's not just a matter of patience and sample complexity. It's also a matter of survival in many cases. That's why we have parents. So especially in robotic systems, this is a pretty critical issue because physical motion can be damaging to the robot. Okay, so there are a couple ways of getting at this. One way to get advice from an expert is to get a reward function, or even to get multiple reward functions. Like, for example, if I was teaching you to play chess, I could give you the reward function that says 0 unless you checkmate your opponent, or I could try to give you a less sparse, more dense reward function that says +1 every time you take a pawn, +3 every time you take a knight, +8 every time you capture the queen, and so forth. And so that's a way of giving really a reward function that's more dense, and that's a way that trainers can help. Essentially, what we're going to talk about today is learning from demonstrations provided by an expert. So, for example, if we have a vehicle like this that we'd like to train to navigate successfully, one way to do it is to give reward functions like -1 every time you brush against the side of a tree, and so forth. But we could also just take the steering wheel and drive the car and let it observe what we're doing as it perceives the environment. And so it can obtain in that way state, action, reward sequences, just like the ones we've talked about, except if the person driving knows what they're doing, then these will be examples of a good policy to try to imitate. So that'll be today's focus. So this is called imitation learning, and there really are two, broadly speaking, two approaches that we're going to talk about today. One is what you might call supervised learning. I see this slide is just saying what I already said. Here's what I want to say. There are two, broadly speaking, two kinds of approaches we'll talk about. One is very direct. The teacher can simply show you, in this state, you should perform this action. In this state, perform this action. And that becomes really a supervised learning problem, as distinguished from the reinforcement learning problem that we've talked about generically. Right? So in a supervised learning problem, we're trying to learn some function. In this case, it'll be the policy from states to actions. And we call it supervised learning if we have training examples of the form, here's the input to the function and here's the output. And of course, in reinforcement learning, instead what we have is often a sequence of delayed training signals from the sequence of actions that we perform, which makes it a more difficult problem, function approximation problem, than if we have simply input-output pairs of the policy function that we're trying to learn. So that's one class of approaches we'll take a look at. And the other is more indirect, where, in fact, what we might try to do instead is use the expert actions that we're observing to infer what their reward function is, and then use that as the basis for training ourselves. Now, why wouldn't we just have the expert type in the reward function for us? Well, depending on what the expert is good at, it might be hard to type in a reward function. Like if you have an expert tennis player, they might say, well, the reward is hitting the ball until your opponent doesn't. But it's harder for them to maybe type in a quantitative reward function to tell you exactly what's a better way to swing than another. They might be able to watch you swing if they're a good tennis instructor and tell you, oh, you should bend your knees more when you're doing that and don't stoop down. But it's hard to, that kind of advice might be easier for them to give. But in general, typing in a reward function can be very tough. Yes?
Even if you successfully learn the reward function, don't you still have the same problem of like learning the policy to go with that reward function, so you're back to like square one?
You're kind of back to square one. So we're going to assume for part of this lecture, we're going to assume, yeah, we have a subroutine that knows how to, given a reward function, solve for the optimal policy. So that'll become a subroutine in some of these algorithms. Yes?
So in the direct method, there's no way you could possibly make the expert demonstrate their response for every state. So it will work to the states that it is shown, right?
Yeah, very good point. So one of the problems we're going to encounter here is that experts are not infinitely patient, so they're not going to give us examples of every state what we should do. We're going to have to rely on generalizing. And one of the things that saves us, especially in robotic kind of applications, is that if you think of all the possible states of the world could be in, like this room, you know, physically there are a lot of weird states it could be in. But you and I have been here long enough days during the last couple of months to realize that it's a very small fraction of the states of the world that are physically possible that actually we encounter here. And furthermore, if you're, so that's going to help us. All we really need, in the same sense as when we do supervised training, what we really need is a training distribution of states that's representative of what we're going to encounter during test time. And if you think about control problems, one of the nice things about control, like let's say driving, is if you think of all the positions your car could be on a road, and then you think of the distribution of positions where your car actually is with high probability on the road, which it would be like going forward in the correct lane as opposed to going backward in the incorrect lane. Then actually, because it's a control problem, we get to choose the state distribution by our actions. And that tends to lead to even more skewed state distributions than if we're taking them randomly generated by the world. And so that skew helps us in terms of the distribution we actually have to sample from the trainer. But it's still an issue. It's a good point. Yes?
In the indirect approach, aren't there like many reward functions you can learn?
There are. And in fact, there's not even a unique reward function given a set of actions that you observe the expert do. So there are all kinds of difficulties with doing this. The first time I heard somebody talk about this, which was around 2000, I thought, that's an impossibly difficult problem. But in fact, I've been proven wrong again since then. So people have made progress on this. Okay, and when I say, for the purposes of this discussion, when I say experts, I might mean a human expert or some other computer program that's very good that I want to emulate instead of the expert. And that might even be a collection of experts, for example, that are good at different subspaces of the problem space. But the point is, could be a human, could be a computer. Okay, so here is the first example of this kind of work that I had seen. This is done by former CMU PhD student, Dean Pomerleau, who is also a former CMU robotics faculty, who is also a former successful startup company generator in the area of automated driving. But for Dean's PhD thesis in 1989, he had the idea that he should train a neural network to steer a car. And so he built a simple single hidden layer neural network. Here's one version of it. The input was based on a camera mounted by the rear view mirror of the car looking forward that would get an image like this. He used a 32 by 32 grid of pixel intensities to code that, and also had a rangefinder that would just scan and find obstacles at a distance. And so he trained the neural network to take that sensory input as the input to the network, and then the output was really a steering command encoded almost like a one-hot vector, but not quite. So you could think of the 45 direction output units as indicating should you drive straight or a little bit to the right or more to the right and so forth. So if you imagine a one-hot encoding where everything is 0 and there's a single 1, what he actually used was, instead of a one-hot, he put a Gaussian around that, so that if you're supposed to turn this direction, he would code it as a 1 in that direction and then a Gaussian decaying values elsewhere. Just for engineering reasons, that worked better. But then he trained this by driving the vehicle around and collecting data, and also replaying in simulation some of those videos. And he got a person to provide the steering actions. So, the simple version, person's in the car steering, the car is sensing the steering direction. And so now for the policy that you want to learn, which is literally this neural network, it takes the observed sensory readings as input, and it's trained to reproduce the steering commands of the user. So he tried this, and it kind of worked, but the single biggest surprise was that even though, and by the way, he tested this out on Route 28 north of Pittsburgh. If you've ever driven on Route 28, you know what a crazy idea this is. And this was at a time, in 1989, there was a lot of work going on, much of it at CMU, on self-driving vehicles. It was in a very early stage of research, and most of the work involved driving robots around in Shenley Park next door on the narrow paths. And so the vehicles at that point would go like a maximum speed of maybe 10 or maybe 15 miles an hour, faster than you would typically walk, but not highway speeds. Dean actually changed the whole story by driving, his vehicle ended up driving 55 miles an hour on Route 28 north of Pittsburgh. So it was a really quantum jump in the technology at the time that he did it. But the single biggest surprise was that when he got out on the road and let the vehicle steer, for the first few seconds it would do fine. But then, it's just a computer, and it would drift one way or another. And once it drifted far enough off the center line, it actually, out of the lane it was supposed to be in, it actually didn't know how to get back into the lane. And if you think about it, and you think about the distribution of training examples that a good driver would be showing, that makes perfect sense. Because the system had been trained on a distribution of states that would be generated by an expert driving policy, and yet it wasn't quite an expert, so eventually it would drift, its errors would accumulate, and once for every accumulating error, it got further and further from the kinds of states that it had been trained on in supervised training mode. And so that led Dean to this comment in his paper. In addition, the network must not solely be shown examples of accurate driving, but also how to recover once a mistake has been made. Partial initial training on a variety of simulated road images should help eliminate these difficulties. And in fact, what he ended up doing was writing a little program that took the images that he had from the good driving, and he would just translate those images to the left or to the right and calculate the compensation, the steering direction that you should take to compensate for those synthesized training examples. And so this was a way of him taking one distribution of examples that really did represent the state distribution you'll get if you drive well, but then perturbing that so that he had more representative examples of edge cases, literally edge of the road cases, so that the system could have examples to train on for that. And that made a big difference in the performance. But you see, in the terminology we're using in our class now, by the way, in most of today I'm going to use O instead of T to represent the observed features of the state rather than S for the full state. Mostly because when we're talking about robots, they don't really get to observe the full state, but just some observations from their sensors. But you can see the kind of thing that would happen. If you have an expert trajectory around some racetrack, and then you let go of the wheel and let the vehicle take over, if it makes a little bit of an error, each time those errors will accumulate. And so the real problem here is that the distribution on states that we get from the pi star optimal policy is different from the distribution of states for the policy pi theta that we're learning. And that's the source of the problem. And this is actually different from supervised learning. If you think about it, if you recall back in your first course in machine learning, where we talked about PAC learning results, we were able to prove that with probability at least 1 minus delta, a program that's shown M training examples in supervised training mode will produce a classifier whose true error is no worse than epsilon, provided, and what did we say? Provided the train distribution and the test distribution are the same. They don't even have to be known. The PAC results say, as long as there's a fixed distribution, we don't even have to know it, then we can get these delta epsilon bounds on how well we can learn. But even though we're using supervised learning methods like training a neural network in supervised mode, we're not actually in a situation where these distributions are the same. And a big part of the problem is that in many cases when we train, say, a supervised method for diagnosing patients, it's fair to assume that the training examples are IID, independent and identically distributed. But in this case where we're generating a sequence of states and the errors are accumulating, really these are not IID examples anymore. And we've seen that previously in the course. That's why we keep this memory buffer and resample batches of training examples from long ago as well as recently. But this is really the heart of the problem. And so one solution, which is common, is to just change the distribution that we train on by augmenting that distribution with examples that are more like the ones we're going to encounter when the actual policy is executed. So if you think back to importance sampling and reweighting examples based on their probabilities, you can imagine a whole family of approaches that you can take. And indeed you can. But it turns out that a fairly straightforward approach works pretty well, which is, oh, I see. Yeah, which is illustrated in this more modern version of Dean Pomerleau's work. There's a nice paper that came out in 2016 from the NVIDIA team, where they used, of course, NVIDIA GPUs to train a deep network that could run lickety-split and at frame rates steer a car. And their network, unlike Dean's, had 27 million connections, 250,000 parameters. But like Dean, they trained it with supervised training. But they also, and they say in their paper, this was inspired by Pomerleau's work, training with data from only the human driver is not sufficient. The network must learn how to recover from mistakes. And so you can see what they did was, in addition to having the driver drive and collecting those examples, they also synthesize examples where they adjust for the shift. They both translated to the side and they rotated to generate synthetic examples. And for those examples, they had a good enough simulator to calculate what the correct steering direction would be to get back onto the road. And so they do this sort of thing where they now mix a combination of actual training examples with synthesized examples. And it leads to a nice video. Oh my goodness, did I not? Oh, I didn't. Oh, I feel bad. Oh, it's okay. We'll skip this video. We'll have another one in a second. If we have time, we'll come back to this video. But it leads to a nice video, which if you search on Dave2 driving a Lincoln, you'll see this on YouTube. And you can see the car driving, and you can see even feature values that are computed inside the network as the car is driving. Feature values like this. So this, for example, shows what the forward-looking camera sees on top. And then as this says, this is the activation of the first layer feature maps in the neural network. And on the right is the second layer feature maps. But you can see, just even looking at these, that it's getting these weird road-like shapes. And you can see it's actually training in a nice way to do this. So I bring up the NVIDIA thing because it's a modern example, but in fact, it's trained, again, with this mix of actual and synthetic examples. And the reason those synthetic examples are so important is they make the training distribution much more like what the test distribution is going to be. Okay, so this leads to a very simple to implement algorithm called Dagger, which looks like this. And the idea of Dagger is basically to iteratively get more and more training examples that are going to be, again, representative of what the policy trainer needs to see in order to handle the distribution of cases it's going to generate. And here's what you do. So first you get some human data, and you train your pi sub theta on that. Here I'm using U as the symbol for actions, by the way, which is kind of standard terminology in control theory. So you can think of U as our old S, or our old A, and O as our old S. So you get a bunch of state action examples from the human. You train your policy, pi, then you run it. So for example, imagine you're running it around the track here. And then what you do is you ask the human to label the examples that you're generating with that policy. So basically, the key issue is that the distribution of states generated by the expert policy is not the same as the distribution of states generated by the learned policy, pi. And so this is a way of simply saying, let's run the learned policy to generate the states, the observed features of the states. And for each of those, we'll ask the human to label the correct action. Now we've got the distribution of states, not from the expert, but from the policy itself. And then we take those and we merge them in with the data we had before. And then we go back and we retrain our policy and iterate on this. So this turns out to be a pretty nice, efficient way of collecting data that will help learn the right policy without pestering the trainer more than necessary. So that's kind of corrections. So that's the Dagger algorithm. And it still has a couple, leaves open a couple of problems. One is that we're still executing a possibly unsafe policy which could drive us off the road into ruin. But the second is that we're still pestering the user. We're still asking for a fair amount of data. And depending on the importance, it might be worth it. Yep?
So the labeling in this case is the user judging it, or are they put in a simulator and asked to just correct the motions?
Yeah, so there are a couple ways of doing this. You can, a typical way is to capture the data and then put it basically in a simulator and let the user, for every single state, you could have the user steer the way they want to steer, for example. And then if you do it in that way offline, it also gives you a chance to slow down the replay, which could be really important if you're, let's say, doing high-speed racing. And that it might be tough for the user to actually just keep up and give the feedback at frame rates. So it's kind of an art, but often it's done in sort of capture and then label rather than doing it in real time. But, people do both. Katerina, feel free to jump in on any of these questions. I think you've maybe got more experience than I do in especially the robotic applications of these.
Right, so in this case, they did play it on the simulator to record, let's say, the human. And in fact, there's another paper with exactly the same methodology for driving a drone in a forest. And they do discuss on the paper how awkward it is to replay the same episode and ask this label from the expert human. So it is hard labeling to go back and replay that. Because also the human gets scared and does a very abrupt motion to put the drone back in. It's not like, take it a little bit more.
Right, humans aren't used to that distribution of states either.
They're also unused, exactly, yeah. So it's an awkward labeling process there.
Yes?
Is this typically a very long process because you have to first train with human data distribution and update the distribution, train again, and keep iterating? How many iterations do you typically have to do?
I really don't know. Do you have a...
You see that you do not drift anymore. Yeah, sure. Each time you go and ask humans, it takes time, right, to record the...
Yeah.
But like how many iterations you'd have to go through for this. I was looking at some videos on YouTube of people doing Atari game racing kind of things. And they were showing examples of after 25 iterations of retraining with Dagger. And you could notice a qualitative improvement in the policy change. They weren't saying there how much data they collected on each iteration, but I assumed it was something like they drove until the game killed the car, and that I assume that was one iteration or one sample, and they said, well, we retrained after 25, here's what it looks like, and it was visibly better. So there are a lot of very cool videos out on YouTube for looking at, especially video game versions of this to see what's going on. Okay, speaking of cool videos, here's one. People use this approach for training a flying robot, which is here, shown here. It's a drone. And they wanted to train it to fly through the woods without crashing into trees. And so there's a cool video that I hope we'll be able to see and hear. Yeah, good. So if I go down to here. And maybe. So that's what it's supposed to do. So here's the expert input. And they use Dagger, this algorithm, to refine. Okay, so this is the view from the drone. Color bar shows the policy-driven command. These are the features from, low-level features from visual input. They're getting things like optical flow, which they say correlate. Edges, the images. And so using Dagger, they train this using an expert to help. And as the video shows, it's able to traverse parts of the terrain that were not part of the training set. So it's generalizing somewhat appropriately.
Some drones must have been destroyed, right?
What's that?
Each time there was a mistake, a drone was destroyed.
It's a sad thing. But total trees avoided, you see. They didn't say how many trees were killed in the preparation of this, or drones. Okay, so there's one from our own Robotics Institute heroes. Okay. All right, so it is hard, in fact, even in that case, to generate the correct feedback when you can't get the sensory data back on the effect of your actions, right? So you're kind of doing this, if you're doing this without a simulator that's simulating the effects of your actions, then that's a problem. Reaction time can be an issue, and so as I mentioned, one solution to that is to play back the experience in slow motion. And, right, we still have imperfect policies, so it's expensive to train in the real world. Okay, so anyway, one approach, and you can see a couple examples of it there, is if we want to learn a policy from demonstrations, we could train the policy directly. And the key issue we have to worry about is that the distribution of states over which those training examples are drawn tend to be different from the distribution of states that our imperfect policy will generate. So you see algorithms like Dagger give us a way of somewhat efficiently capturing data from experts to get the right distribution. Let's talk about the other approach of reward function learning. So the idea here is that, if you think about our reinforcement learning typical setting, we have some reward function in mind. Maybe we have a forward model of the dynamics. And then given those two things, we have a variety of reinforcement learning algorithms we talked about in the course. Their job is to find a policy that maximizes the expected future discounted reward, given that policy. And then it takes action for each state. And so the idea of inverse reinforcement learning is to given this and actions from the user, let's solve for what their reward function must have been. So that's the general setup for inverse reinforcement learning. So we still have a state space and action space. Let's assume we have the dynamics. We know the next state function, which could be probabilistic. We have demonstrations from the teacher, but we're not told the reward function. And so our job is to see if we can recover that reward function from what we are given, and to use that reward function to find a good policy. And this behavior cloning is a phrase people use for talking about what we just supervised training method that we just looked at. So here's the general framing of inverse reinforcement learning. And here's a way to think. Suppose we have some robot like this one up here in the corner. We have an expert who teleoperates that vehicle, let's say, gets us some examples. And so one way to think about it is that expert generates a sequence of state action pairs while they're operating the system. And we could say that Y star is just the trajectory data that we observe when the action is done. And we could say, well, what if we assume the reward function itself is some linear function of some features extracted from this trajectory? So you could think of this as being some feature vector which is computed from these. It doesn't have to be exactly those. It could be computed, say, even by a neural network. A bunch of features of the state. And if we assume the reward function is some linear function of these calculated features of the state action pairs, then we can say the problem of learning the reward function is the problem of learning what this set of weights is, if in fact we predefine what this feature vector is. And this is a common simplification that is used widely. The simplification being that it's up to the designer to come up with good features of the world, and it's up to the reward estimator to come up with the weights on those different features. Okay? So if we think of it that way, then we can go back to basics. We could say, well, our job is to find a reward function, let's call it R star, which is the one we attribute to the trainer. we want to discover what that is. And what's the property it would need to have? Well, this is the property if you think about it. We want to assume that the expert knows what they're doing. For example, suppose they have a reward function and they've got the optimal policy. Then what will be the property that their reward function will satisfy? It'll satisfy the property that every other policy is not as good, or at least not better than theirs. So this is that property written down. What we're saying is that we want a reward function R star, that's the one we're looking for, such that the expected value of that over the optimal policy, the policy of the expert who's training us, that expected value is at least as great as that same reward function controlled by any other policy. And that should be true for every other possible policy. So this is just a way of saying the property that defines the reward function of the expert, if we assume the expert actually optimizes it, is this property. That it's the one such that the expert actions outperform all other policies. Okay, does that make sense? Because this is really the key. Yes?
So in the last slide, the feature vector, was it derived from every state action combination, or was it a function of the entire trajectory?
Here we were saying that each of these feature vectors is, well, in this schematic, each feature vector is computed at a single time. So it's a state action pair. And then we're saying Y star is that sequence. So here I'm saying F of Y star, so generically I'm saying that, but in this example we're assuming it decomposes into the same weights applied across time to different time-specific features. And this is the framing that we're going to go with for a couple slides now. Okay, so everybody comfortable with this? Yes?
I am, but it also means you'll never do better than the expert, right? Because you're assuming the expert is as good as the expert.
That's right.
Yeah. And the expert also can never tell you I shouldn't have done that, right? Because you're assuming that everything they did.
That's right. That's right. So here, and those are both really good points. So here we're assuming, the problem framing is really this, that this is what we're given and we're not given any other information. So in that case, really, it's probably, you could probably prove that it's unsolvable to determine whether the expert is, well, I have to be careful. You don't know whether the expert has the right policy, and you don't know their reward function. Therefore, you're kind of double blind, and it's hard to get everything right. We will see an approach where we can avoid saying that we're learning the reward function, but we can still guarantee that we get to be at least as good as the expert at it. Okay, so this is the property we're after. We're searching for a reward function that satisfies this. Now, if we assume the reward is linear over some features of those state action pairs, as we suggested in that previous slide, then let's see what happens. Then we can say, well, the reward associated with any given state, sorry, I left out the action, for any given state is just some linear weights, W, times the feature vector that we're observing of observed features for that state. And so now I can say the thing we're trying to optimize, or the expected reward for a given policy, factors in this way. I can rewrite it first by pulling the weights out of the expectation. And then calling this expectation, which is really under policy pi, this is the expected value under policy pi, under the state distribution generated by policy pi, of the feature values discounted in time according to where they are in the sequence. And so if I call this distribution of discounted future feature values mu, then I can rewrite the reward function as a linear combination of these discounted future feature values. And so now I can see that if I go back to the property we agreed we want, which is that the property that the expert's reward function satisfies is that it gives a better expected reward than any other policy would. And if we substitute now for that this, then all we really need to do is find a set of weights such that the distribution mu over discounted future feature values is greater than that same weight applied to the mu that we'll get over the distribution of those same feature values under other policies. What's nice is that we started by saying some property that was going to be hard to evaluate, which we agreed was correct, but it's going to be hard to evaluate because we don't know what R is. But if we make the assumption that the reward function is a linear function of the feature values phi, and we define mu as the discounted future sum of feature values, then we can show that this is equivalent. And the nice thing is, this is something we can observe. We may not know what the reward function of the expert is, but we can observe what features occur as the user is operating the device. And so now we can solve for W in terms of this. Yes?
Is the expectation done differently on the left and the right? The left is like expectation for one policy, and the other is the expectation for a different policy?
No, actually, these are both.
I mean, for like the second to last line of the slide.
This one?
Yeah.
So in both cases, there's a for all pi applying to this, and a for all pi applying to this. I should have bracketed. I should have put a square bracket here and a square bracket here. But for every pi, we want this to be the case, and for every policy pi, we want this to be the case. So it is the same. Does that make sense? Of course, it could be expensive to find every policy pi. Okay. So the key new feature here is that now we're talking about not the expected discounted future reward, but simply the expected discounted sum of feature values. And given those, we're going to be able to solve for W's that satisfy this property. Okay, so I see. Okay, so sorry, so it leads to. Okay, let me take these in sequence. So just to be clear about how we would get this distribution on future expected feature values. If we had an expert training us by driving the car, the robot, or the device, and they create m different trajectories, then what we're going to do is we're going to average over all those trajectories and every time point in each trajectory to get this. We really are interested in the expected value of this discounted future features with respect to the state distribution that's implied by the policy. So we're going to sample multiple trajectories and look at every state along that, just to be clear. Okay, so now here's a nice observation that's due to a paper that you really should read. I haven't put this up on the website, though the slides are. I'll put a pointer to this paper up on the website, too, as one of the 2 readings. But they point out that for a policy pi to be guaranteed to perform as well as the expert policy, that should say pi star, it suffices that the feature expectations match, to approximately match. So the one norm here is just the sum of the features, by the way. So basically, even if we can find a way to make these features match, then we can know that we're mimicking the expert policy to within epsilon, even if we don't know what the expert reward function is. Right? So this basically licenses us, if we want, to even find a different way of matching the feature distributions without even going through the intermediate step of calculating W to figure out what the reward function is. So which is pretty cool, if you think about it. This is assuming that your reward weights stay less than 1 also, so that the rewards stay in the range from 0 to 1. But which is not really a real constraint, because you could just scale everything down. So this is an important thing, and here's the simple proof of it. So why would we wish to find a pi hat such that the distribution on future discounted feature values is close to the expert, mu e is the expert generated distribution on future discounted feature values? Well, for such a pi squiggle, we would have that for any weights that are at most 1. The difference between the expert policy pi e and our arbitrary pi squiggle will be, and this first step is what we already saw in the previous slide. I'm just rewriting that as the expected reward is the weights times the distributions on the discounted future feature values. And we can rewrite this because x times y is less than the norm of x times the norm of y, less or equal. So we can factor it. And then the second line just follows from the fact that we've put both of these to have norm 1. And so when you, this will be less than 1 times epsilon. So basically, it's easy to show that what we're showing here is that if we find a pi such that its feature distributions match those of the expert to within epsilon, then its expected reward will also match to within epsilon. So it's straightforward math, but the significance of this is it really says that, okay, it's good enough just to match not the features of individual states, but the discounted future features. So we're taking into account the trajectories. So we're really matching properties of the trajectories rather than properties of the states. And that's enough to let us do mimicking, imitation learning without, if we can find a way to do that without even estimating W, that'd be fine too. Okay, so here's an algorithm that Abil and Ng use. Again, they're assuming that the reward function is a linear function of some features. And then the algorithm is just pick some policy, pi 0, and then go through an iterative loop where we're going to refine that policy each time, guess the reward function. That is, find the reward function such that the teacher outperforms our current policy and all the previous ones we've considered in earlier iterations. And one way to say that is we want to obey the constraint that we've talked about before, that the weighted feature values for the expert policy is greater than the weighted feature values for the others, because that's what gives us the knowledge that the expected reward is greater by some margin. And this must be true for each policy that we've considered so far. And so this, when we solve for this, we're basically finding the weights for the reward function. We know the reward function, we can, here's the subroutine, invoke our known reinforcement learning algorithms to learn the right policy for that reward function. And now, if this margin is small enough, if the distance between these is small enough, then we know we've actually found to within epsilon the policy that would give us the same reward as the expert policy to within epsilon. And otherwise, we just go back and we pick, we iterate again, we pick another policy and generate another reward function. Yep?
How did we use the property that we learned in the last slide that you don't really need the weights?
We didn't use it here. So here we're actually literally solving for the weights. We're solving for the weights to solve this optimization problem. So here we are explicitly calculating weights, getting the reward function, and then finding the right policy according to that. Okay, so when they did this and they applied it in a simple grid world, not unlike our little robot grid world where you get rewards in different parts of the grid, they compared this kind of inverse reinforcement learning using that algorithm to supervised training, the first approach we talked about today. And the two curves that dominate are variants of the inverse reinforcement learning algorithm. And these other three are different ways of doing supervised learning. And the horizontal axis here is the log of the number of sample trajectories. So you can see here that in terms of sample complexity, this kind of inverse reinforcement learning, where we're estimating the reward function, instead of just supervised training the policy, actually is dominating by far in terms of sample complexity. Okay? All right, now, one thing I didn't mention is how do we solve this optimization in the problem in the middle? And again, if you think back to your Introduction to Machine Learning course, you should recognize that form of problem. That's the same form of problem we state basically when we do support vector machine calculation. It's a constrained optimization problem. We're trying to maximize the margin between these two values, and we're picking, it's the max over our possible choices of weights. So we want the weights that will maximize the margin between these two quantities. So in fact, we can use essentially the same algorithms that we use for support vector machines to solve that problem. You can think of, here's a typical support vector machine thing where we have two classes of points and we're trying to learn the classifier that best separates them. And the classifier is represented by a weight vector. And we choose that weight vector to maximize the margin. So here you can think of each point as representing a policy. And the point is that quantity that we measured for the policy, the expected discounted future features of the policy. And I guess I should show it under that interpretation, I should only have one black dot, which is the expert policy. And then the white dots would be the different other policies that I've considered as I've been iterating and trying to get more of them. So basically, we can use the SVM maximum margin algorithms to derive the weights, and those weights will be the ones that maximize the margin, the distance between W times these points and W times the expert policy. And again, that's exactly what we're looking to find. The weights that will give us the maximum margin between the weights times these kind of points versus the weights times that kind of points. Yep.
I'm confused as to why we want to find the maximum margin between the optimal policy and our policy rather than, like, shouldn't we be trying to minimize to get closer to the optimal policy?
Here, let's see.
Or are we trying to maximize the distance from the policies that we've learned previously?
Yeah, we're trying to find the weight that will make the expert as far better as possible from the policies that we've considered so far. So we're trying to maximize our esteem for the expert.
Oh, okay. So it's more like we're trying to learn the expert, not trying to learn the other policy to match the expert.
Right. We're saying that let's make the most reward. Let's pick the W that makes the expert's actions most rewarding.
Okay.
And then we can, relative to that reward, train ourselves a new policy. So it's this little competition each time through our loop. We're going to re-estimate what the reward function is and make the expert as the headroom between our other policies and the expert as large as possible. And then we're going to use that reward function to train a better policy.
Okay.
For labeling the points as an expert policy or not, wouldn't you only have one point for the future expectation of the expert policy?
Yes, and so that's why I said when I got to this, I really should only have one black point under that interpretation. Right.
This diagram is a generic SVM diagram.
Right, that's a generic SVM. But under this interpretation, there'd be many white points, the not expert policies, and there'd be just one black point. Okay, so once you go down this road, you can see that we can generalize this in a couple ways. For example, we could add in another term where instead of saying we want to, here's the standard maximum margin problem. Instead, we could frame it by adding in another term that tells us basically our preconceived idea about the distance between pi star and pi. So the idea is that the margin, we'd like it to be larger for policies that are more different from the expert's observed policy. And so, for example, once we have a sample of actions done by the user and we've derived the full policy pi ourselves, we can apply pi to each of the examples we know from the user and look at the number or fraction of states where pi disagrees with the action choice. And so in that case, this is a way of bringing in that additional information that has to do with not just an individual state at a time or an individual trajectory at a time, but the entire state space, really. And so for that reason, this is sometimes called the structured prediction max margin. We can also generalize to multiple MDPs or, I guess I first should say we can also do the usual SVM trick of changing the optimization objective to allow slack variables. That is, to allow there to be cases where we observe the expert policy not dominating us. And that, of course, could be true if the reward function is probabilistic, for example. So we can bring in slack variables the same way that we do in support vector machines. And we can also sum over multiple MDPs and policies. So if you think like if we have, here's a good example. Suppose we have some trajectory planning thing from different initial states or even different final states, but in the same world, and we want a single policy to deal with those. So then we can generalize that way too. Okay, so this gives us a way to see this. So all this comes from all this comes from that simple idea that all we really need to do if we want to mimic the expert, if we're willing to assume the reward function is a linear combination of these features that we can observe, which is a big assumption, then we can mimic the expert in this way by literally re-estimating the reward function, re-estimating our policy. So I'll just give one more example of this that grounds out a little bit differently. This is taken from the second reading, which I'm going to recommend to you today, called An Invitation to Imitation by Drew Bagnell. And this just is a sketch of his own work on trajectory planning. And in this case, they're controlling a robot in off-road navigation. And they had an expert drive the car. And they're trying to learn the policy. And the way they set it up is that the perception system, there's the caption, I'll just read it basically. The perception system gives us a grid kind of description of the world. And the idea here is that at any given point in the grid, there are features like maybe rocks or trees or texture of the grass, texture of the color of the grid cell, and so forth. And those are features that can be used to assign a cost function or a reward function, if you like, that you will get if you have to pass through that state as part of your trajectory for navigation. And so you can think the features are massaged into an estimate of the traversability, which is a scalar value that describes the reward or penalty of going through that step. So the W that we're going to end up learning in this application is just the W that takes the observed. You can think of each grid cell as a state, take the perceived features of that state, learn a W that calculates the cost of going through that state. Now the algorithm that they use, they just start with a very simple uniform cost function saying every cell is worth the same amount, which I guess would mean you do shortest path if you're trying to plan a trajectory from point A to B. But then they look at what the expert does, and if they find things where the expert and the policy diverge, choose different actions, and they go there and they basically learn another function to add into this that makes it true that the way the expert went will be a lower cost way than the way that the system went. And they, again, iterate that. Each time they find a difference between the expert, they simply update their cost function. And so then they have that iterative process leads to this kind of sequence of trajectory planning. So what you see on the bottom here is a map of an area where the brightness indicates traversability, that is the cost. And on top is the satellite imagery that they're using to calculate these traversability features. And so you can see left to right is time. And so initially, in green, you see their policy takes the shortest path route because it assumes the cost is the same everywhere, whereas the expert takes the red route. And then iteratively, as they're updating their cost function, you can see that it converges to the expert. But this is just another example of that same process of saying, let's assume the reward is some linear combination of these features, and we look at the discounted future. In this case, I think the discount factor, maybe they even use 0, I don't know. Maybe they're using the total sum of costs for the trajectory. Although you could see discounting as a way of taking into account that you might perceive more when you get closer. But basically, they're learning a reward function again. That's a function of the observed features of the state times some linear weights. So it comes out this way. Okay, so that's the idea for today. So to summarize, the first thing we looked at was supervised training, that is learning the policy directly from state action pairs contributed by the expert. The second way we saw is more indirect, where we tried to estimate more globally what the reward function is. You can see that one of the advantages of that is we might be able to generalize better if the observed features actually correlate well with a reward function. We might be able to generalize better than if we're doing straight supervised learning. There's an awful lot more that's going on in this area these days. It's a very active area of research. And so we'll have another lecture. Katerina's going to talk on Wednesday, following up on this and looking at some robot control examples and maybe other things. So let me turn it over to you for...
So one observation is that this discounted expected state features that we saw, especially if they're not discounted, this trajectory will have exactly the same features as this trajectory. Does this make sense? Because we average across the states. So we use these expected state features as a proxy for the state distribution, the trajectory distribution, but it's not a great proxy. Another big approximation we made is this linearity, that we want the reward to be linear over the state features. The question is, can we do better? Can we remove these two constraints? Can we have a better description of our trajectory distribution and state distribution? And can we have a reward function be a general neural network? And the answer is yes. And we'll see this on Wednesday. It's in fact a very recent result that came last year. And it turns out that you don't even need any state density estimation. It looks like this. You have a set of expert trajectories and you're training a policy network that given states tries to imitate those trajectories. You have a second network that looks at what you're generating and looks also at the expert trajectories and tries to give you gradients, guidance of whether the distributions match. We're not going to be averaging across trajectories in this case. You can compute features directly on the trajectories themselves, and I think someone asked this question. And this is exactly generative adversarial networks, the framework of generative adversarial networks, and this line of work is called generative adversarial imitation learning. So we'll see the connection between this framework and maximum entropy inverse reinforcement learning that again came out of CMU on Wednesday. And we're going to talk about trajectory and controllers next week. Let me make one more comment. In this lecture, our experts have been humans. Can you imagine a situation where one model would like to imitate another model? Both of the models are reinforcement learning algorithms. Why would one reinforcement learning algorithm like to imitate another reinforcement learning algorithm? And this is the idea behind guided policy search, which is very, it's a framework that is very famous in robotics. Well, the reason is the following. These two learning models can have very different hypothesis classes. You can have a reinforcement learning algorithm having a very small hypothesis class for the model that is used, which is very, very fast to learn for this particular case, though it cannot generalize. Okay, so as a result, we need to distill knowledge of those very simple hypothesis classes, very simple model-based learners, reinforcement learnings, into a neural network policy. So our teachers are small hypothesis class models, and the student is a high, like large hypothesis class model. This is exactly the opposite that what a famous machine learning researcher, Rich Caruana, proposed in a paper. It's called student-teacher learning, where he had a very deep neural network being the teacher, learned from many, many training examples, and was distilling the knowledge of this deep model to a much shorter model than you can run, let's say, on your mobile phone post-training. So this is exactly the difference between being in a supervised learning regime, where you have tons of training data and you can train deep models, versus in a regime where the rewards are sparse, you cannot afford, you're on a real robotic platform, you cannot afford having many data samples, and you really need to constrain your hypothesis class. And I think the second case is much more close to the way humans learn, or let's say if we ever develop autonomous agents, those would learn through sequential tasks where they incrementally learn as opposed to given millions of supervised examples. So I think this is interesting, but I think for better consequences of thoughts, maybe on Wednesday we should look at this adversarial imitation learning, and next week we can look at imitating controllers. See you on Wednesday.